Today, we are diving into a classic chapter from Fred Brooks's The Mythical Man-Month. It's called The Whole and the Parts, and it's all about one of the biggest challenges in building anything complex. How do you get all the individual pieces to actually work together as a seamless whole? And the key to understanding this, believe it or not, starts with a line from Shakespeare. So, Shakespeare gives us this classic, timeless boast. A character proudly proclaims that he can summon spirits from the depths of the ocean. It's a big, powerful claim, right? But here's the kicker. His buddy comes back with a simple, absolutely devastating question. Why, so can I, or so can any man, but will they come when you do call for them? And that really brings us to the modern-day magician, the software engineer. I mean, it's one thing to say, I can write a program to control air traffic or manage a power grid. It's a bold claim, but making it actually work day in and day out without a hitch, that's a whole different ballgame. And that's the central problem we're digging into today. Okay, so here's how we're going to break this down. First, we'll talk about the boast and the bug. Then we'll look at how to design bugs out from the very beginning. After that, we'll trace the history of finding the ones that inevitably slip through. And finally, we'll tackle the hardest part of all, putting all the pieces together so the whole thing actually works. All right, let's jump right in. Section 1, the boast and the bug. This is really where that grand ambition smacks right into the messy reality of getting things done. So look, we're not talking about your garden variety typo here. The real enemies, the most dangerous ones, are what we call system bugs. These are the nasty little problems that pop up at the seams, where you have two components that work perfectly fine on their own, but when you connect them, disaster. It's all because they were built on slightly different assumptions. This is where the big, complex systems truly fall apart. Okay, so if these system bugs are the real enemy, how do we fight them? Well, the best strategy is to stop them from ever being born in the first place. It's a whole philosophy of proactive prevention. And this quote from V.A. Vysotsky, man, it just hits the nail on the head. The most important work you do happens long before anyone writes a single line of code. Because if you don't have a crystal clear, super detailed, and well-tested plan, what happens? Well, developers will just fill in the blanks themselves. And that's exactly where those deadly mismatched assumptions come from. So, one of the most powerful prevention tools we have is top-down design. It's really just a disciplined way of working. You start with the big picture, the rough sketch. Then, you systematically break it down into smaller and smaller pieces. As you refine each piece, you start to see these nice, self-contained modules. This whole process forces you to spot flaws in the big picture design way, way earlier, before they get permanently baked into the code. And this change in thinking goes all the way down to the code itself. In the early days, programming was kind of the Wild West. You had these go-to statements that could send the program's logic jumping all over the place. We called it spaghetti code for a reason. It was just a tangled mess. Structured programming brought law and order to that chaos, forcing logic into clean, predictable blocks, like if this, then that. You're not just writing lines anymore, you're building something understandable. But let's be real. Even with the best designs in the world, bugs are gonna happen. So what do we do then? Well, let's take a quick look at how our bug hunting methods have evolved over the years. The history here is actually pretty fascinating. Back in the 50s, computer time was so incredibly precious that you had to plan every single second of your debugging session at the console. Then, to save machine time, we switched to just dumping the computer's entire memory onto giant stacks of paper, and you'd spend hours at your desk trying to decode it. As programs got bigger, that became impossible, so we moved to snapshots. And today, of course, we've got these incredible interactive tools with instant feedback. But here's the thing. Here is the big twist. Even with all our amazing modern tools, a researcher named Gold did this fascinating experiment, and he found that programmers made 3 times more progress when they actually sat down and meticulously planned their debugging session before they ever touched the keyboard. It turns out all that instant feedback, well, it kind of made us lazy. So what does that tell us? It means the old school discipline still matters. A lot. A really productive session isn't just about hammering away at the terminal. It's a cycle. You spend time at your desk, planning your attack. Then, you go execute that plan. And, this is the part we always forget, you spend time after to clean up, log what you learned, and get ready for the next round. And that brings us to the final challenge, the boss level, if you will, assembling the whole thing. This is, as Brooks points out, the unexpectedly hard part of the entire journey. We've all felt this, right? That massive temptation to get impatient, to skip the tedious work of testing each little piece and just smash everything together to see what breaks. The story we tell ourselves is, hey, we'll find the really big system bugs sooner. But let's be honest, that's a total fantasy. It doesn't save time, it just creates absolute chaos. Because now you have no idea where the problem is. So where do we look for a better way? Believe it or not, we can learn a ton from our friends in hardware engineering. They've been dealing with this stuff for a long, long time, and they have a deep, deep respect for process and control. They had this brilliant, super simple idea called the purple wire technique. When they found a bug in a hardware prototype, the quick fix would be made with a bright purple wire. You literally couldn't miss it sitting there among all the other yellow wires. It was a physical, visual reminder. This is temporary, this is a patch, and it's logged in a journal waiting for a proper, permanent fix. It's a genius way to keep moving forward without losing control. And that just begs the question for every single one of us, right? When you make that quick and dirty fix in your code, how do you make it visible? How do you make sure that temporary patch doesn't become a permanent, ticking time bomb for the next person? What's your team's purple wire? So the disciplined alternative to just smashing it all together looks like this. It's methodical. You start with a tiny core system that you know works. Then you add one, and only one, new, fully tested part. Then you rerun all of your old tests to make sure you didn't break anything. And only when everything passes do you move on and repeat the cycle. This whole thing requires you to fight that constant urge to rush. The core mindset has to shift from, I hope this works, to, I know for a fact there are bugs in here, and my job is to have a systematic, orderly plan to find and remove them. And this is really the crucial point of the whole thing. System debugging, putting all the pieces together, will always take longer than you think. Always. It is the hardest part of the job. And because of that, it absolutely demands a disciplined, systematic, and well-planned approach. Optimism is your worst enemy here. A solid, repeatable process, that's your best friend. Which, leaves us with one last big question to chew on. This wisdom is decades old, but wow, does it feel relevant right now? In our modern tech culture that loves the motto, move fast and break things, have we maybe forgotten how to build things that don't break? It's definitely something worth thinking about.